Good evening, everyone. Again, my name is Lexus Brinkley-Tapp, and today I will be presenting to you my Masters of Data Science Capstone project on machine learning enhanced quantum approximate optimization for network routing. I will be using this research also in my PhD, and it explores how we can take classical optimization problems like network routing and reframe it into a quantum data pipeline, combining QAOA with machine learning to test what is actually possible on real hardware. So next slide, please. So here is just some details on ethical implications of quantum and data science. The data sets that are used are ethically compliant with no personal identifiable data. So next, please. So this roadmap is going to be the basis of this presentation. We're going to work through motivation, quantum theory, methodology, hardware results, machine learning analysis, and future work. So let's begin with section 1, which is the motivation and content. So next we're going to be going over why you should even care about optimization. As I mentioned earlier, if you think to many ways you can get to work from home, we all know that you can take a million different routes, but we want the best route so we don't waste time, we don't waste money, gas, or energy going those longer routes, or even a route that's invalid, say if there's construction one day. Um, so we want to be able to move as fast as we can, as efficiently as we can. So there are current network drawbacks that can lead to many country counties not and rural counties not getting the adequate bandwidth access. So better routing means direct reductions in energy costs, time savings, and internet connectivity to all communities that need it. So next, please. So now we're going to be talking about the networking problem. This is an NP-hard problem. When we introduce constraints such as multiple paths, dynamic costs, and competing objectives, think of a multi-level labyrinth, like even more complex than the labyrinth that we've seen on the first slide. The state vector of, for example, like a 200 node metro network, it has seemingly infinite valid solutions, making classical exhaustive search a very time costing option. So, and modern networks make this even worse, such as 5G and Internet of Things and cloud infrastructures. They can change their length costs in milliseconds. So, classical algorithms like Dijkstra's waste energy every time they recompute from scratch. Sorry. These consequences can affect equity, again, for these rural networks that I mentioned before, especially in telehealth, emergency services, and remote education can degrade as well. Next, please. So why do we want to go into quantum computing and QAOA for this approach? Classical high performance computing sometimes they can cost not billions, millions of dollars to build, and they require storage and computational requirements that most institutions don't have access to. So quantum computing, especially via cloud API, is an option. There are plenty of quantum services that exist and that are accessible with no rack space or no capital expenditure, and especially for sits on a job. So with the QBO matrix that I will be speaking on later, this routing problem, especially on the 6-qubit processor that I'm going to be talking about, versus the classical optimizer that I use, we're going to go put it against the classical optimizer, and then we will see what's actually accessible with quantum optimization. So these are my research questions. This project sits at the intersection of technical advancement, methodological innovation, and health equity. My 4 research project questions are: can QAOA converge on real hardware? What sizes are feasible on current quantum devices? Can machine learning predict optimal parameters and features? And can this extend to real life network? I'm going to hypothesize. I wanted to hypothesize that QAOA can solve routing problems on accessible quantum hardware with support of machine learning. So now we are moving on to quantum theory, and then we're going to move into the quantum fundamentals. As data scientists, we know a bit is a 0 and a 1, but a qubit holds the probability amplitudes for both 1 and 0 at the same time. So as you can see, this top equation on the screen, alpha ket 0 plus beta ket 0, this is a general qubit state. And when we run a 16 qubit circuit, the processor is explicitly exploring over 65,000 states at the same time. So from a data science lens, we think of this as a representation of an exponential solution space, but it's compressed. Current quantum devices called NICS devices for noisy intermediate scale quantum, they have 10 to 100,000, to 100 physical qubits, making quantum circuits real and accessible as we aim for real error correction. Because our goal isn't to read all of the states, but is to involve the system to choose to make the good solutions be more likely what's selected. So now to our next slide. So the value of QAOA's penalty optimization converts routing rules into a quantum Hamiltonian, and the ground state of this Hamiltonian is the optimal routing solution. So I'm going to break this down with the next slide. So for this deep dive, QAOA works in 6 steps. It initializes all the qubits into equal superposition, and as every routing solution is explored at the same time. So the 2 parameters that control everything are gamma, which tunes how strongly the circuit encodes routing cost, and then beta controls how broadly the mixer explodes neighboring solutions. Then we use the Kabbalah method, which is used to find the values of gamma and beta parameters, pushing the quantum state towards the best routing path. Our next step is to apply the cost unitary, which rotates the quantum phases proportional to the path cost, so low-cost solutions accumulate a favorable phase. Then the mixer Hamiltonian is applied. This prevents the state from collapsing to a local minimum, and we repeat these 2 unitaries a p number of times. And then we measure the number of times the circuit is executed, called shots. I used over 1,000 for this run. And then we get a probability distribution over the potential routing paths. Finally, Kabbalah adjusts the angles and calls the CPU again. And this system evolves the repeated layers. And after the measurement, we get a probability distribution over all the solutions. The cost Hamiltonian encodes a cubo matrix, and it puts it directly into the quantum system. So the trade-off that we get is QAOA doesn't guarantee optimal paths, but it provides a bounded approximation quality on accessible hardware. So next slide, please. So this is the formulation for the cubo. It has 4 Hamiltonian components. The objective function minimizes the total weighted path cost, and penalty A enforces exactly one active node per time step. And this is the constraint that required the most calibration. Penalty B penalizes transitions between non-adjacent nodes, and penalty C forces the path to start at the local source at the source location and end at the destination location. So penalty B and penalty C were fixed at 1 throughout this process, but empirical calibration was required to find the optimal crossover, which allowed the equation to complete the routing problem in a form the quantum processor could read. And again, the ground state of this Hamiltonian is the optimal routing solution. So next, I'm going to show you the quantum circuit. And this is what actually runs on the quantum processor. You see that to the right here. This is alternating the cost and mixer layers on the network nodes. As you can see in the graph here, it's just the basic 6-node network. So it moves across the nodes and the edges, and then it measures the results. The circuit uses Hadamard, rotation, and CNOT gates to entangle the qubits and to enforce the pre-mentioned constraints as before. So next we're moving on to section 3, then which is the methodology and pipeline. So for the next slide, this is the complete pipeline. As you can see, I use the Snap repository. I will use the Snap repository for my data sets, and that's where I have my networking problem. And then we'll go and get into the qubit encoding, the Qiskit circuit on IBM's cloud, IQM's cloud API. Then we're talking about the Kabbalah optimizer, and I will be using XGBoost as my machine learning model. The full stack is Python with Qiskit, IBM, and XGBoost, all in a Conda environment. Next slide, please. So the data sets that I use are 3, again, real-world topologies from the Stanford Network Analysis Project repository. The first is a scientific collaboration graph. Next is a scale-free enterprise network, email network, and then I have a sparse peer-to-peer network. I use these 3 data sets because the data was topologically diverse. It was hierarchical, and the scale-free structures allowed me to generalize the test. It also allowed me to benchmark on over 200 instances, spanning from 400 to 200 from 400 to 200, 40 to 200 qubits in the simulated step. The path links were from 3 to 6 time steps, and the classical optimization solution computed by Dijkstra's algorithm was used for validation. Next slide, please. For the penalty weight optimization, the chart at the top visualizes the instance size and the path cost distributions. The chart at the bottom, it shows the penalty sensitivity for our main parameter. So when our parameter A is below 0.47, the constraints violations dominate the circuit, and the algorithm produces invalid paths. At exactly at 0.47, there is the critical crossover, since that's when the valid paths reach 100% and the solution quality is preserved. But if we go above that, the penalties dominate and quality degrades. So that's why the 0.14 is the sweet spot for this penalty optimization. Next slide, please. So now we're going to talk about the actual hardware results. Next slide, please. So I was able to use IQM series quantum computing unit. It has a 6-qubit capacity, and this hardware was assessed via cloud API using Python code, and I also use IBM's Qiskit quantum library for the circuit creation and the gate setup. Next slide, please. So the convergence of the circuit's cost function, it started at a random value of 10.07, and the optimizer explored parameter space. As you can see, these spikes and in the iterations between 3 and 6, it means the Kabbalah optimizer was searching for the best results. So by iteration 6, it found a good solution, and that's where it converged at 3.41. And this shows that the QAOA converges on real quantum hardware. So we have a 133% improvement time. It only took 140 seconds, and we were able to get the final parameters of gamma equals 3.41 and beta equals 1.05. Next slide, please. So now we're going to talk about the machine learning results. So this model was trained using XGBoost as a simple baseline for future models. XGBoost was used to predict optimal gamma and beta from the problem features. So I used the input features of the number of qubits, the path length, which was k, the number of nodes, and the number of edges in the network. XGBoost was used because it handles tabular data without scaling and is robust for smaller data sets, and it's interpretable. It's able to interpret feature importances pretty good. And I just wanted to use it as a transparent baseline as for future work when I move into more robust models. Next slide, please. So the results for my machine learning was gamma R squared value was a negative 0.23, and beta's R squared value was a negative 0.16. Now, this means that the model performs worse than just predicting the mean, but the reason that this matters is it's not necessarily a failure, but a diagnostics for the future. It's telling me that the scalar features contain not a good sign of aren't a good feature to predict the quantum parameters. So my next step is to replace XGBoost with maybe neural networks. That's my next goal. And to see if I can train it on centrality and clustering coefficients so that it'll know better how to move throughout the network and move throughout the edges. So the cost of this landscape is shaped by the network structure, not the size. And so, like I said, that's where I'm going to be moving into more compatible machine learning models. Next slide, please. And so this is the future work section. So as I was stating before, the 133% cost improvement on the real hardware with zero constraint violations, it converged at 6 with P equals 1. And again, if we missed that part, P is basically the number of layers that we alternate between with the cost in a mixer Hamiltonians that I spoke of. And the hardware, like, even though it was 6 qubits, it was still not enough for me to get the full results that I could because quantum is very high scale. So it's difficult to get precise precision results at the moment, but we're getting better and better. And so, and again, this isn't a weakness of this model. It just shows that I need to change the methods for the next phase of this pipeline, and especially as we move towards grounding it in equity and making sure that we can serve the communities that need to be served. So next slide, please. And so here I detail some of the cybersecurity considerations for quantum, especially with the threat of quantum cracking cryptography. So it's vital to care ethics that we keep data sensitive in with quantum being used. Next slide, please. So for the future work roadmap, as you can see right now, I started with just a p-value of 1 on a 6-qubit processor. So I want to move up to a higher processor like the IQM's Garnet, which has over 20 qubits, or something like, IBM's Eagle, which is something similar. I also want to use even more data sets and again explore more machine learning models. And then once I'm able to validate that process, I want to again grow my qubit count, use a multi-layered QAOA framework, And there I will see if there's potential to run targets on like rural community connectivities as each step builds on the one before. Next slide, please. So as a new quantum researcher, this QAO demonstration began with a poster that on simulated data at the Southeastern Quantum Concert last fall in 2025. This led to a follow-up with Oak Ridge National Laboratory and an internship coming up this summer. There's also a IEEE publication that was approved and more manuscripts to come. Next slide, please. So the takeaways for this presentation is quantum works on real hardware without using high performance computing. Also, even though the negative R-squared values was the research finding, it just shows that the scalar features aren't sufficient and that we should be moving towards graph topology, specifically neural networks as the next step. Then the same framework also has potential scales to biological networks. So care ethics again and quantum computing can produce a pipeline that is basically equitable for the community at large. Next slide, please. And that is the end of my presentation. I want to thank Dr. Chatterjee as my advisor, Dr. Ghosh for funding this research, and our quantum and AI labs, especially Jackie for presenting and for helping me with all my quantum work, and the Meharry SACS community at large. So thank you all for your time. And I'll take any questions.
Question.
So
Yes.
it's not a question. Let me see. Oh, okay. It is excellent job. Okay. I thought it's a question. Yes, please.
I was going to say, I apologize if you hear anything in the background. I was going to say, when you combine machine learning with quantum computing, and I was reading your presentation, but you kind of went fast a little bit. But it was saying that it could break encryption in algorithms. Do Does doing this research scare you a little bit to know that it could in the future break encryptions and basically it could really break a lot of HIPAA laws, like a lot of information because it could break encryption. You know, it could expand into all kinds of cards and social security numbers. Don't that scare you a little bit doing this research?
I do understand that it can be a little scary, which is why there are so many researchers, particularly like um Mikkel, that are focusing on quantum cryptography and how we can get ahead of the people who will want to use quantum hacking for evil instead of good, instead of protecting data, they're trying to use it. So I just think the more research that we do, that's what's going to make the threat less of a threat. But it definitely should be something of concern. Brian?
Yeah, I just wanted to say, Lexus, well, great presentation. And I kind of wanted to kind of respond to Michelle a little bit because I just went to a seminar for someone that it was a professor that was involved in quantum. And pretty much what they're saying is that this is the next step up from our traditional internet that we have now. So essentially 10 years from now, whether or not we know it or not, quantum will potentially be running the internet. So I kind of don't know if we have a choice in that sense, because from what she was saying, that this is the direction we're headed in. So just a comment I had.
I agree.
Okay. I think in that regard, we need some safeguards so that they cannot do certain actions, you know?
I agree. Mikhail, you had a comment?
Yeah, I was gonna add to that too. Like I put in the chat, like our research is kind of complementary, and like what you were saying too, Michelle. When I was doing my research, it kind of was like I wouldn't say scary, but kind of surreal. Because a lot of work, what I was doing, as I understand, like the quantum concepts more, kind of remind me of stuff you see in like sci-fi movies and things like that. So, but that's kind of what I'm doing with cybersecurity and quantum and data science combined. So yeah, we have those safe roles that we're working on going
They are
forward.
complementing each other. One is doing for
It's
the
very,
distributed computing part, one is doing the security part. So, and fortunately, both are coming back in the fall. So we could have something really great from the group. And yes, one more thing to add, that Lexus is going to Oak Ridge as RSI fellow, and she will be directly working with the HPC quantum lab of the Oak Ridge. Hopefully our students will get more insights when she'll be back. So hope for the best.